session with Jan Albert, and he'll be telling us also about some Bootstrap ideas, but for Mesons at Jan.
Thank you. Hi, everyone. Thanks for coming. I also want to thank the organizers for putting together this nice workshop. Such a wonderful place, and for inviting me to speak. So yeah, today I'll tell you a bit more about this story that I've been pursuing with Leonardo back at Stony Brook. It's this program of bootstrapping Mesons in the large unlimit. And some of you may recall a short talk that I gave back at NYU in the meeting in November. Today, since I have a bit more time, I'll walk you through some more details of how we get these bounds. And then I'll discuss these most recent results that came out last December. So the talk will be loosely based on these first two papers that I wrote with Leonardo, but mostly I'll focus on the results of this most recent paper that we wrote in collaboration with Alessandro Vicky from Pisa and Johan Henriksson from Saclay. Okay. So I want to start a bit with the basic picture. I'll do it on this board, and then I'll get to the results on the screen. So our target is QCD in the large unlimit. So just to be precise, we take NF flavors, so NF quarks, in the fundamental, and we will take them to be massless. So we're going to work in the chiral limit. Okay, just so we're in 4 dimensions, and then we take n to infinity, the number of scholars, in the 2th sense. So we keep NF fixed, and actually my bounds are going to be independent of NF, so we don't need to fix any number of flavors as long as it's fixed. Only send n to infinity. And then about this chiral limit, this is for simplicity, so that we have massless pions, but it would actually be relatively straightforward to leave this assumption, and we could also give some mass to the quarks and then to the pions. Okay, so this is the target that we want to understand, and we're going to do that with bootstrap techniques. So the key feature of large N is that the different asymptotic sectors asymptotic states of the theory decouple. Okay, so we have the Mesons, QQ bar, we have baryons that are Q to the N, and we have blue balls that are schematically these color singlets. Okay, and their interactions are suppressed by powers of 1 over n. So in large N, we can focus on them separately. And we're going to be focusing on the Mesons, which is what we've been doing so far. But I want to stress that it would be also relatively straightforward to extend our methods to glue balls. We would just have to change the kinematics of open strings for those of closed strings. And baryons would require some more care because they become infinitely heavy at large N. Nevertheless, it would be very interesting to study. Okay. So today it's just Mesons, and that's all I'll have to say. I will only have things to say about Mesons. And the other key feature of large N is that all their interactions are suppressed by powers of 1 over n. Okay? So in particular, we'll focus a lot on 3-point couplings of 3 Mesons, I, J, and K. I'm going to denote this, the coupling constant for this, as lambda I, J, K. And it follows from simple counting arguments that this scales like 1 over square root n. Okay? So in the strict large N limit, they are free, they're not interacting. And then we're going to be working at leading order where only 3 level interactions survive. Okay? This is the limit of large N that we are going to be working at. Okay? So now this theory at large N becomes parameterized by the following data. So I'll write it here, yes. So we have an infinite collection of Mesons, starting with the pions, then the rows, and whatnot. And these are parameterized by their masses, spins, and possibly other quantum numbers. And then we have these on-shell couplings, IJK, and perhaps even 4-point couplings and higher point couplings, although they won't play a role today. Okay? So we think of these data as parameterizing the theory, a space, or you can think of these as the coordinates of some infinite dimensional space of putative large N theories, and then one particular value for these parameters will be QCD. And the question is, how can we find this point? Okay. Now, one approach is to put this on the lattice and compute these couplings, but and some of them have been computed this way, but we will proceed in a bootstrap way, and we'll put bounds on these couplings. Okay. So how does this work? We're going to be using a version of the S-matrix bootstrap, which it goes under the name of positivity bounds, but I won't get into too much details. But the basic idea is the following. So S-matrix. So the bootstrap problem is to consider the scattering amplitudes of all the Mesons in the spectrum. And right now, we can only consider 2-to-2 scattering amplitudes. So I have I, J, K, L. And then you compute the amplitudes with these putative parameters, and then you impose some consistency conditions that these amplitudes have to satisfy. For example, crossing and unitarity. And then there's some other assumptions that I'll discuss, but you could keep making this list longer and longer. And then the idea is that we use these constraints on the amplitudes computed with these parameters to put bounds on these parameters. Okay, so what we're going to get are, we're going to pick some slices, so some parameters, and put bounds on those. So for example, we'll have plots like, so bounds on some unshell couplings and some masses, and they could look something like this, with some allowed region, some disallowed region. And this is carving out the allowed space. So healthy theories that satisfy our list of assumptions have to live in this allowed region. And then the goal of the bootstrap is to corner, well, in this case QCD, but physically interesting theories. So what does that mean? It means that the dream of this bootstrap approach is that in some features of the boundary, say, so along the boundary, and perhaps in some king or something, lies QCD. So this is a hope rather than an expectation, because if this is the case, then we can use the bootstrap solution, which tells us information about the boundary, to extract information about QCD. But this doesn't have to be the case. It will be that QCD is well inside the bounds. And then the idea is that you have to start making more assumptions or more restrictions for your amplitude to try to shrink these bounds and put QCD on the boundary. So we're not claiming that crossing unitarity and these few assumptions will nail down QCD. The hope is that you can start putting more assumptions to try to shrink this down. Okay, and that's the game that has to be played.
You're imposing a favor symmetry from the beginning?
Yes, I'm going to do that. Yes, I'm going to assume that there's a favor symmetry. But one thing that's interesting is that you can also impose that there's an anomaly, for example, and these sort of things that we can motivate from the QCD Lagrangian. Yeah, and on that note, I wanted to stress that this is not a new approach. In fact, it predates QCD, but back in the day, with these very few assumptions, they were hoping to get QCD, and that was not successful. But now we have more systematic ways and better tools to implement this more systematically, and that were developed mostly in the context of the conformal bootstrap. And also we have the motivation from the conformal bootstrap that they've managed to find in similar looking plots the Ising model or other physically interesting theories in some boundaries. Okay, so this is the basic logic, and we're trying to understand things better of QCD or put bounds in these couplings and try to corner QCD. Any questions about the logic so far?
Was it in Reggie behavior as well?
Yes. I'll get to that in a second. Okay, so as well. Okay, so we're gonna in principle the bootstrap problem involves scattering all the Mesons in your spectrum, but we need to start somewhere. So we start with the lowest ones, which are the pions. Okay, and pions in this chiral limit are massless because they're Goldstone bosons of chiral symmetry breaking. So UNF left times UNF right is spontaneously broken to UNF diagonal, and then this produces some Goldstone bosons, which are the pions, and therefore massless. We're going to be scattering these, and then the first thing you have to do is parameterize the amplitude, and that is quite easy at large n, because only diagrams with the topology of disk contribute. So we have pion A, pi B, pi C, pi D, where this is the flavor index. And then, since only diagrams with the topology of disks contribute, the full flavor dependence will come in a single trace of the generators. TA, TB, TC, times some amplitude, which is only a function of Mendelssohn invariance. Okay? So this is the flavor order amplitude that looks roughly like the scattering of open strings, and this is the one that we're going to be putting balance on. Okay? So how does this work? So I'm going to list a bunch of properties or assumptions, if you wish, that amplitude M of SU satisfies, and then we're going to use those to put bounds on these on that data over there. Okay? So here are the properties. The first one is crossing, and that's in this language is just the statement that M of SU equals M of US. And the reason for this is that you require that the amplitude is invariant, and they're exchanging the labels of identical pions. And since it's open strings, it's only SU symmetric rather than fully STU symmetric. The next one is that it's meromorphic. And that's because we're working at large n, so only tree-level interactions survive. So if we plot the complex plane of this, so this amplitude in the complex plane, so the usual plots, complex S at fixed U, we will only find poles on the real S axis, that correspond to all the exchanges in the theory. So here would be the row meson, that's the first exchange state, and then there's other mesons in the spectrum. So each, just to be clear, each of these poles corresponds to a diagram like this, which has this form, lambda, so the coupling between two pions and some meson I squared, and then there's a Legendre polynomial that captures the spin, some theta, and then there's the propagator that captures the mass. Okay? So it's in this way, in these singularities, that all that data is encoded in this amplitude. We have the mass, the spin, and the...
I mean, if there's massless particles, you have continuum, you are exactly meromorphic next to 1/n, so you don't worry, that doesn't...
That's strict 1/n leading order, and yes, right? Because there's no pion exchange.
Right.
So you're thinking about...
No, I'm just saying, M is equal to 0, they're massless states.
I'm lost. The pions are massless. Right, but they don't show up as intermediate states. Right, that's right. Yeah, so I'm working at that. Yeah, everything we'll have to say will be in this leading order in N where it's meromorphic.
I'm just wondering about the 1/n corrections.
Oh, understood. Yeah.
Problem there with the continuum in this whole bootstrappy approach.
Yeah, I mean, I'm relying heavily in the large N limit. I mean, for one thing, like you have also like double trace contributions and so on.
Worried about log infinity times 1/square root of n.
Mm-hmm. Yeah, I don't have much to say about those at this point. Thank you. Okay, so the next one is unitarity. And that's just that norms are positive, and in this language it's just a statement that these couplings are non-negative. Then the next one that I'm going to require is Regge behavior. This was mentioned before. So the Regge behavior is just a question of how this amplitude grows in the Regge limit. So the Regge limit is this kinematic regime where I send all around the complex plane a fixed u smaller than 0, and we'll take it to be small. Okay, and then it follows. So for QCD-like amplitudes, it's known that the growth is controlled by the intercept of the leading Regge trajectory. So if we plot the spectrum of the theory in this sort of plots, let me put it here. So I'm going to plot the spin and the mass squared. Then the spectrum of the theory looks something like this. There's first a row meson here that has some mass, the mass of the row that sets the scale of the problem. Then here there's another resonance that's called F2, and then they continue, and you can arrange them in Regge trajectories. And then there's a bunch more down here. But the leading Regge trajectory is the one of the row, and it has intercept below 1. Okay? So this growth is in this regime is polynomial, and it's with a power that's below 1. Okay? So that's all we're going to assume, that if you divide this amplitude by s and you send s to infinity, it goes to 0. Okay? And then the last bit that we're going to use is the fact that this amplitude admits low energy expansion. Okay? So let me explain what that means. Low energy expansion. So if you look at this plot over here, you see that there's a region here around the origin, or the amplitude is in the middle. Okay? So down here, I can use a Taylor expansion, so I can use the polynomial expansion which converges, which has radius of convergence corresponding to the mass of the first state. Okay, so this looks something like this. On low energy, you have the most general polynomial expansion you can write down. And we write it like this, s plus u. And I'm using crossing symmetry already. So if I'm just writing a crossing symmetric polynomial, and I'll write a couple more terms. Okay, so all I'm saying is that it's analytic around the origin, and here I can use this polynomial expansion. But this is actually very physical, because all it's saying is at the level of this is a statement from the amplitude's point of view, that this theory admits an EFT description below some cutoff. So this cutoff is the mass of the row, and for energies below this cutoff scale, I can integrate out all the mesons in the spectrum, and what I produce is an EFT for pions, which is described by this 4-point coupling. So this term here is nothing but a 4-point contact interaction with order 2 in derivatives, and these two terms are the same but order 4, and then I would have higher and higher derivative terms. Okay, and just to stress, these are not unphysical. These are actually the Wilson coefficients of the chiral Lagrangian, which is the EFT4 pions. So in particular, this term here is related to the kinetic term of the chiral Lagrangian, this familiar term. Okay, and then the other ones are related to the Wilson coefficient, the higher term. Okay, so this one will play a role. The other is not in this talk. Okay, so just to recap, we have this amplitude that describes pion scattering at large n, and we impose or require that they satisfy these properties, and then we're going to use this to put bands on the different data. Okay, so very quickly.
I'm not assuming any of the structure that comes from chiral perturbation theory.
Sorry, could you?
For example, you're not assuming that the EFT is just. What are you assuming about chiral symmetry?
Yeah, so I mean, I don't know.
You can say what you're assuming about flavor symmetry.
Yeah, so I'm assuming that
You are assuming.
Yeah, I'm assuming that it's flavor ordered already.
Okay, so that's the flavor, the non-chiral symmetry. What about the chiral symmetry?
Sorry, this is the chiral symmetry, right? Isn't it? So these are it's a flavor symmetry, the SU and F.
That's SUN, but not SUN cross SUN.
Oh, yeah, I understood. Yeah, no, right. I mean, it's hard to input that. I mean, so one way that we did it was by upgrading these to form factors, where you have external photos that are so yeah, you turn on background gauge fields for these UNF.
For example, I mean, I think one of the results you'd like to claim is that you get the Adler zero or something.
Okay, yeah, sure.
But you're not putting that you could put in a sense if you just wanted to calculate F pi.
Yeah, okay. So very good point. Yeah, I was sweeping that under the rug. So there's an issue with the Adler zero is the fact that I haven't written a constant term here, and that there's no contact there. But there's actually a subtlety, because if I assume spin one right behavior, this drops out from this relation. So here there would be a G0, and I set that to 0, and that would be the Adler zero constraint. And that unfortunately is outside, so we cannot even claim that. So indeed, it's sort of little what we're imposing of the fact that these are Goldstone bosons. But there's something that we can do when we consider form factors, and there's other terms, so there's generalizations of this Adler zero, because there's some terms that involve the charge matrix that you would write down from here, but that are actually 0. So that we've managed to impose. But it doesn't seem to give very sharp results, so I haven't highlighted them too much. But it's bits by bits that we managed to input this information.
And in addition to pions, you have massless eta prime here. Right?
Yes, I agree, yeah. So I haven't written S and S because we're at large n, so the U1 axis is actually mixed in here. And this thing is actually NF squared. So it includes the NF squared minus 1 pions plus the eta prime, which is massless, yes. So yeah, because we're in this, it becomes massless in the unit. And any more questions?
In practice, what is your answers for the Ricci trajectory?
Yeah, I'll show that in a second. We make different assumptions. We're usually agnostic about most of it, and then we'll start including resonances one by one. I'll show that in a second.
What about the region of negative U?
The region of what, sorry?
Negative U, minus time U.
Oh, we are always around, we are always at around 0. So we explained the forward limit. So we don't assume anything about down here. It's actually hard to implement. So Sasha discussed this the other day, like this sub-exponential, exponential softness. So the fact that as you keep going down, it keeps going down. That's what happens in string theory. But it was hard to impose in the bootstrap in their case. But
That's probably not what happens in string theory. But even the square root behavior doesn't happen in QCD.
Right, no, clearly. We don't impose anything like that. I was just going to say that if you even wanted to do it,
It doesn't come into the calculations. You don't come in.
what you could do, yeah, I mean, the Ricci behavior would be alpha of u or t, whatever, and then as you keep going down, you'd be allowed to do further and further subtractions. That would be a way to do it. The issue is that if you actually want to put it numerically into the bootstrap, there's some technical issues that prevent you from using it. So there is a way to probe it, but we're not assuming it because that's clearly not what happens in the...
There is a way to probe it, but there are technical issues.
Okay, so we can write down the analytic expressions, but we cannot actually put it into the computer in a way that spits out. So there's the constraints that we get oscillate, and then the numerics throw them to 0. So there seems to be a technical obstruction. I cannot obtain meaningful results right now, but in principle, there's a way to. We have analytic control.
In principle, the bootstrap approach could put tell you something about the large negative T limit?
No, I think it's something that you could input by hand if you had some other. You need other ways to tell that, but there's a way to probe this. So, okay, I'm using the wrong word. I'm just saying there's a way to input this by doing these expression relations. That's all I would want to claim. Yes. So. Right, so all I want to say now is that with this, how we're going to use these assumptions to put bounds on this data, okay? And it's very simple. All we do is write down a dispersion relation around, so it's a contour integral around infinity of the amplitude over enough powers of x. And then if this is greater than 1, by the Regge behavior, this has to be 0, okay? So what we're drawing here is a contour integral around infinity. It has to be 0. And then what we can do by analyticity, or the fact that it's meromorphic, is bring it down. And then there's a pole from the subtraction down there, the denominator, which we pick up. And then there's the contribution from all these poles down up here. Okay, so by doing that, we obtain the link between low energies, where we can use this low energy expansion, and high energies, which contains this data that we're interested in. Okay, so what this produces for you are something called sum rules, which just express the low energy couplings, those couplings down there, in terms of high energy data. So sum over the spectrum of the coupling squared times some functions that we know explicitly, that depend on the masses and the spin. And then moreover, you can obtain something called null constraints, which include crossing symmetry, which is a statement that since these couplings appear with two terms by crossing symmetry, you will actually obtain two different sum rules for the same coupling. So by subtracting the two, you obtain some expressions that look like this. So some 0 has to be equal to something that is not explicitly 0, and that puts some constraints on the high energy data. So these functions f and n we know explicitly, but they're sort of long. We don't want to write them. But this is basically the two sets of relations that we use to put bounds. Okay. So once we have this, what we can do is recast these relations into a semi-definite programming problem, like was discussed in the previous talk. And I'm not going to walk you through the algorithm, but I can give you more details if you're interested. And then the way this works is we make an assumption of the spectrum, and then we feed this into the computer, and we use a solver to obtain a functional which then puts bounds on these couplings. Okay? I know this was a bit fast. I can provide more details later, but now I just want to jump to the results. So in our first paper, what we did was put bounds on these couplings, but those gave some corners and so on, and none of them were QCD. You can find those in our first paper. But today I wanted to focus on our newer results, which are bounds on these couplings themselves, the on-shell couplings. Okay? So this is the first such plot, and let me explain what we're seeing. So this is the assumption. We assume that there's an explicit row meson at mass of the row, which sets the scale. And then we assume that there's a gap after that, which we're gonna scan over. And after that gap, we allow for any location, so any spin and masses for the mesons, okay? And then what I'm plotting here is an upper bound for the on-shell coupling, normalized by powers of f pi squared. And this normalization is important if we want this to remain finite in the large n limit. Okay? And then I'm plotting this upper bound as a function of the gap. So when the gap is at 1, I touched it. We're up here, and then when I push the gap, I'm moving in that direction. Okay, so we see that the allowed region is this one here, and any theory, so any values for this data that is consistent with our assumptions must live inside this area. Okay, so now again, what was the philosophy? We've carved out, well, this is the allowed region in this two-dimensional size, and we would like to see QCD on some bound to see if we can say anything about it. But that's very unlikely. So what you can do is go and compare to experiment. And I should stress that we would love to compare to lattice results. But as far as I'm aware, there are no lattice results for this coupling and for this cutoff here, which would be the next resonance after the row. And the best we can do right now is compare to experimental QCD, which of course you should take with a grain of salt because we are large n, and this is for n equals to 3. Right? But in any case, so it's inside the bound, so that's reassuring. At least it's not, we haven't ruled it out. But it's not quite close to the boundary. So the next step is let's try to understand what this boundary is and see if it's something funny, try to kill it and try to go push this bound farther. Yeah.
I mean, it wouldn't have been a contradiction if that had been ruled out because of
No,
the margin.
exactly,
right?
yes, yes. Yes.
Well, except that this scales with n, so 1 over n squared, this is 1 over n, I guess it is 1 over n corrections.
Right, yes.
Or not 1 over n squared.
I believe so because they're
Yeah.
mesons.
That would be surprising.
But, right, so,
Why don't, and you don't assume an omega, an omega pole?
omega is degenerate with the rho because it's a single, yeah, in large n
So
they're
when you
degenerate.
say you put in a row, you put in I equals 0 as well.
Yeah. So, yeah. Sorry, I equals 0. That's
Not
single.
just put it in, as a spin 1, you put it as a spin 0 as well. You put
Yes,
it in
yes.
full.
A full
UN.
yeah, 40. But actually for any NF, it's always UN. So and now I'm going to discuss something called the F, and it's also with the A meson. They're all together in NF squared multiplets.
This is avoid the NC to the 0, right? This ratio.
Yes. This is 1 over square root n squared, and then f by squared goes like f by squared goes like n. So yes, that remains finite. Okay, so what are these corners? So this corner up here is just a funny amplitude that you can write down. And
So
it
what do
would,
you mean by corners?
yeah, sorry, this point here, we understood what amplitude explains that point, and it's just this, which is a very simple amplitude that you can write down. The product of two poles, you can check that it's positive, crossing symmetric, and has the right ratio behavior, and it looks like this, which is not a very physical amplitude. However, it's still saturating the bounds. And then as you start moving along the bound, what happens is that the rho remains, because that was our assumption, and everything else gets pushed until you reach this point down here, where you have another funny amplitude that looks like this, where you've pushed everything to infinity, and you keep only this guy. So the punchline is all this bound is explained by very simple solutions, and we'd like to go beyond those if we need to find anything like QCD. Okay. So this motivated our new assumption, which is our most recent results, where we include the first spin 2 meson. And that's important, the fact that it's spin 2, because we're assuming a spin 1 rigid behavior. And the rho meson was borderline okay. So the reason those simple solutions existed was because this was borderline. So a single rho meson is not okay. It has a rigid behavior exactly 1, and we're assuming it's pretty better than that. But it can still, you can still concoct these funny amplitudes. But if you assume something with spin 2, it grows really bad, and then the bootstrap has to work really hard to find a solution.
Why don't you assume a spin 0?
Yeah, so spin 0 completely decoupled precisely because we're doing spin 1 rigid behavior. So even if I do it, all my bootstrap solutions can remove it. And that's actually why the full, so this amplitude has a spin 0, but to get the extremal point, you actually have to subtract it, which is something you're allowed to do in this bootstrap. So scalars, unfortunately, are outside our domain. Yeah. And then, okay, so with this assumption, I can make the same plot. For the onshore coupling of the F2, and again, the F2 is the same as the A meson because they're degenerate. And then it looks something like this, and here I've shown in more colors more numbers of null constraints. So more null constraints make the bounds only stronger, and you see that this area has converged, but these two still have not converged, and then it becomes numerically harder to make them smaller. But you see that this point has converged converges really fast, so it suggests that here there's some solution. And then from the bootstrap, we're like, okay, let's try and understand this king. And the first thing you do is compare to experiment, and to our surprise, it meets very well the mass. So this is saying that whatever this solution is, it has a new resonance at this mass, and this is the same that happens for QCD. Okay. However, it's still not quite at the same amplitude, but so at the same ratio of these couplings. But in order to probe that, what you can do is look at another slice, where I'm plotting the same horizontal vertical axis, which is the onshore coupling of the F2, versus the onshore coupling of the rho, so the two poles that we have. Okay, and now the king corresponds to this point here. Oh, sorry, there's a question.
You fix the mass of F meson to some value that you didn't specify?
Yes, I fixed the experimental value, yes. So that's, and now there is one parameter, indeed, one dimensionless parameter that I have to fix, and I fix that to the real world. The solution doesn't change much if I play around with it. So this bends a little bit to the right or to the left, but there's always a king. But in order to compare two things, we've fixed to the experimental value. Thanks. Any other questions? Sorry, speak up if I'm not looking. Okay, thank you. Right. So on these other slides, the king corresponds to this point here, so you can see clearly that there's some king. And QCD, experimental QCD is well inside the bounds. But what's surprising is that it actually has the same ratio. So it's on this, it falls very well into this line. And that means that the ratio of the two couplings for this solution and QCD is the same. And the nice thing about this ratio is that it cancels out the normalization. So you could think that perhaps what we have is the right on-shell couplings, but somehow the f-pi changed. And that's something that would happen, for example, if you remove scalars. So if you give me an experimental QCD solution, I can always remove scalars, and that would make this smaller, and therefore pushing that out. So what you can hope is that what we have actually found, this is still a hope, but the best you can hope for is that this is QCD minus some things, perhaps scalars or perhaps more. We'll see that indeed there's more missing. And yeah.
Yeah, the shaded region is the allowed region, right?
Mm-hmm.
So which max is corresponding, how it gets changed when you face different max?
Right, this is converged already.
So this is the maximum.
Yeah. So I did a few, and they kept coming in, and I'm just showing the result. I don't remember what value it
So
is.
it converges very fast.
Yeah, relatively fast. So it's around n max 17, the next one. So you see, because we're at this point that's already converged. Yeah, thanks for the question. Okay, and then the last thing we tried to do, and I'll try to keep it short, is try to understand the spectrum from SDPP. And so SDPP is the solver that we use to obtain these results. And then you can get to this point and try to extract information from it, and then compare it to QCD. So at first it looks like a mess. These are the two we inputted by hand. There's some neat trajectory that continues, but there's all sort of stuff up here that you don't expect at all in any QCD-like amplitude. But then you can convince yourself that these are actually spurious poles from the fact that we are truncating in various places. And for example, you can make another assumption, and you say you can move these spurious poles around, but the trajectory doesn't change much, and the solution doesn't change. So by iterating these games, you can find that up to a very high spin, there seems to be a single rigid trajectory, which is something sort of surprising, because we find, first, it's not linear, this trajectory, and second, there are no daughter trajectories. So we don't know of any such amplitude in flat space, but this could just be an issue of the fact that we're doing 4-point bootstrap with just a single pion, like with only pions. And now we're trying to repeat this story where we have not just pions in the external state, but also row mesons. And then the hope is that by doing this more constraining story, we might actually be able to probe daughter trajectories. And then just as a treat, what we did was to compare the spectrum to QCD. And again, we would love to compare to lattice results, but they're only available for spin 1, as far as I'm aware. If somebody knows for higher spins, please let me know. I'd be very interested.
Say it again?
Yeah, so, sorry, I'm speaking really fast.
Take your time. I mean, you have questions. We started 5 minutes ago.
All right, thank you. So we would love to compare the spectrum to results from lattice QCD at large N. As far as I'm aware, these results are available for various for various mesons of spin 1. They're not for spin 2 and higher. And it would be very interesting to have them for these trajectories, which involves rows and Fs. So this would be a row 3, this is an F4, and so on and so forth. It'd be very interesting to compare to that. But the best we can do right now is compare to PDG. And this is the comparison. And so you see the row and the F2 match, no surprise, because we inputted those by hand. But the row 3 is the one that we were getting quite right. And then to our surprise, the F4 and the row F5 are close enough. And then the F6 is pretty far away, but these two are actually not confirmed when you look at PDG. So, okay. Yeah.
What are the orange?
Yeah, sorry. The orange are my solutions. I was painting them blue before.
These are going to the kink point, the
Yes.
so-called kink point.
That's right. So there was that king point. This is the solution that the bootstrap spits out. So it's telling you there is an amplitude that looks like this, which lives on that point. And then we're comparing that to QCD. So now change colors, and those blue points are these orange points, and now these black points are PDG, experimental results. And it's surprisingly a good matching up to spin 5. And what's also surprising is that these points are deviating from a linear trajectory, and this seems to be keeping track of that. Now, it could all be a huge coincidence. Again, we're a large N, this is experimental, but it's still a surprising coincidence. And yeah, the thing, so indeed, like this seems to at least accommodate the picture that we might be getting closer to QCD, where we've subtracted something, and that something is all the daughter trajectories, which is a bit too much. And then, yeah, we're looking forward to these results for mixed correlators, which in the case of the conformal bootstrap was very powerful. And yeah, there's more things that we're going to try, but yeah, you can ask me later if you're interested. Yeah.
To add what? Mixed correlators?
Yes, mixed correlators. Yes, mixed scattering, a system of mixed scattering amplitudes between pions and other excited states. So, like the row meson would be the first test, and later you could do F2 and so on. And this is analogous to what happens in the conformal bootstrap, and that's why I'm applying the correlators. I'm sorry. Yeah.
You know, in the old days when the bootstrap was first done, long before QCD, long before string theory, people tried to derive flavor symmetry, if that was sort of came out of the bootstrap.
Uh-huh.
So relaxing your assumption of flavor symmetry and just looking at, you know, particles, lots of particles, n particles. What does the bootstrap, does that imply? Here, you're trying to reproduce QCD, but have you ever looked at that kind of question? Are there non-flavor symmetric? You just relax that, and
I think
many more couplings, it's much harder.
Yeah. So it could be done, but I think I don't think there's any hope we'll actually derive flavor symmetry from that, because all we have is an amplitude. Like they could be just scalars in. Like if I relax flavor symmetry, I don't have this open string picture, and all I have is like you could have like closed strings, and then that could just be the amplitude of some scalars in any other theory. So I don't think. I mean, you'd have to be impose other things if you want to get flavor symmetry out. Our philosophy is to take the QC Lagrange and take as much as we can. And
Obviously.
yeah. No, but we haven't tried. And yeah, that's all I have to say. Thank you.
You haven't considered doing multi-particle beyond.
We have thought about it a lot, but it's quite hard because then, there's many more Mandelstam invariants and so on. So right now we don't have the technology, but it's certainly in the to-do list.
The problem with doing the higher states is, of course, that breaks down completely once you go to the next order one over n.
Yes.
Yes, you go off and do it.
But I mean, wouldn't it be nice already to have the strict large n?
No, that's the advantage of doing multi-particle. So that there is a systematic procedure.
Right. Yes.
Those external particles are stable, at least you don't have to. At some point, you're going to run into sums of self-energy graphs, and your poles are going to move.
When you have 1 over n correction. Yes. Agreed. Yeah.
Is it surprising that the large n answer agrees so well here? I mean, do you have some feeling for why the corrections are so small? Or?
There's arguments saying that I think it's usually the case that some large n results seem to match with real world better than you would expect. And then you can argue that the coupling is not actually 1 over 3, but there's factors of pi and whatnot. And in the case of globals, it's even squared. So I don't have. It's surprising to me, at least, but I don't have people have tried to argue that it's not so surprising, but I'm not those people.
Yeah.
Okay, so no more questions. We'll thank the speaker again.